Writing a concentration equilibrium constant expression. So the key to writing equilibrium constant expressions is that you are essentially going to take the concentrations of each of your products raised to the power of their stoichiometric coefficient in the balanced chemical equation and divide by the concentration of each of your reactants, each raised to the power of their stoichiometric coefficient. Remember, this is for homogeneous equilibrium. Okay, so notice that all the reactants and products are all in the same state of matter, right? They are all aqueous solutions. So only aqueous reactants and products are going to appear in the concentration equilibrium product expression. So to write our generic equilibrium constant, so K, capital K just means equilibrium constant. If there's a subscript, that's telling you what flavor of equilibrium constant it is. So a subscript C is telling you that is an equilibrium constant in terms of concentration. You will also meet K subscript P, which is where instead of concentrations, you use partial pressures. So again, thinking about homogeneous equilibria versus heterogeneous equilibria, if you're writing a equilibrium constant in terms of partial pressures, you're only going to include gaseous reactants and products in that equilibrium constant expression. Okay, other types of equilibrium constants you might meet are KSP, so solubility product. So that's referring to an equilibrium about solubility. K subscript A, K subscript B is acid and base dissociation constant, so ionization of acids and bases. So weak acids, weak bases, we know that's an equilibrium problem. Okay, so let's get back to concentration. It's going to be the concentration of your products. So I'm just going to use a generic form of this first. So for any reactants A and B forming products C and D, you're going to have the concentration of product C raised to the power of its stoichiometric coefficient in the balanced chemical equation. So we're going to get that a little c times the concentration of product D, again raised to the power of its stoichiometric coefficient in the balanced chemical equation. So we're just going to get that little d divided by the concentration of reactant A raised to the power of its stoichiometric coefficient little a times the concentration of reactant B raised to the power of its stoichiometric coefficient, which is going to be little b. Okay, so this is our generic form for any equilibrium constant expression. And remember, especially when you start getting into acid-base dissociations, etc., we're only going to include aqueous stuff. I've just realized my line that I'm trying to draw is not showing up because it's white. There we go. Okay, so let's do it then for this equation. So, capital K, please. What are our products? Always start with your products because the products go on top. Concentration, the first product will be our acetate ion, CH3COO minus. That'll be raised to the power of its stoichiometric coefficient, which is 2, multiplied by our other product, CH6O2. Stoichiometric coefficient is 1, so something raised to the power of 1 is just itself, and then divide by reactants, so C6H10O4. Make sure they're all aqueous, only aqueous things are going to appear. Okay, stoichiometric ratio is 1, so no power there, just the power of 1, times the concentration of hydroxide, and that will be raised to the power of 2. So that's it. That is our concentration equilibrium constant expression. Okay, so if you actually had the concentrations at equilibrium, you'd substitute that in and you just get a number for the equilibrium constant expression. Be careful with units because the units are going to be affected by those stoichiometric powers, right? So units are not always going to be the same. Also, if you're in terms of pressure, those will be partial pressures. And watch out for heterogeneous equilibria. Like, so if one of those was a solid, for example, or liquid, solids and liquids are not going to appear in that equilibrium constant expression because you can't define their concentration or their partial pressure. If you're not at equilibrium and you substitute in concentrations or partial pressures into an equilibrium constant expression, what you're going to get is the reaction quotient Q. And comparing that to the actual value of K is going to tell you more about the direction that the reaction is going to proceed in order to reach equilibrium, whether you need to produce more products. Okay, so that's going to increase the value of Q until it approaches K. So we have to travel to the right, or if we have to produce more reactants, which is on the bottom of that fraction, so we're going to have to travel to the left to increase that number for the reaction quotient and end up at equilibrium concentrations.